So good afternoon. My name is Mahmoud Hachem. I'm an engineer with Degenkolb, and I'm going to present to you an overview of the state of nonlinear analysis as it's done in practice today. So I won't show you any development of new models or new materials. It's going to be examples of how we use nonlinear analysis. We use a variety of software, OpenSees being one of them, but it's definitely not in exclusion or not the primary software we use. We'd like to move closer to OpenSees and use it more, and hopefully that's in the future for us. I'm a member of Degenkolb's New Technologies group, and if you don't know what that is, we're a small group in Degenkolb. And we do research, we do development of tools, and we bring in new software and technologies. And here's a list of the various topics we work on, the tools we're generating. Degenkolb being an earthquake engineering firm, it really touches on all aspects of earthquake design, nonlinear seismic history analysis. So we're developing tools to develop hysteretic properties. We're doing research on ground motion selection and scaling. We're starting to work more on soil structure interaction. We're developing tools for post-processing. So we're developing something called the Degenkolb Design Database for post-processing of performed results. We're developing risk products. We also do component modeling, finite element analysis of connections, and so on, in addition to a number of other projects that we have going on. We have a core group of about 4 people. This includes Mark Sinclair, myself. Sylvia Mazzoni used to be a researcher at UC Berkeley. She worked a lot on OpenSees. So when she came to us, she brought to us a lot of her experience on OpenSees and some of the tools that she's developed over time. So here's an outline of what I'm going to be talking about. We'll talk a little bit about nonlinear response history analysis, why we do it in practice, and what are the various tools that we've developed to improve efficiency, to manage the models, and so on. We'll talk a little bit about soil foundation structure interaction. I'm going to mention also building Tickle, which is a tool for OpenSees. It's a user interface that you can use with OpenSees to model buildings. Sylvia, again, developed that. And we'll wrap up with some tips on when to use response history analysis and some opportunities and challenges with OpenSees. So in design is an iterative multi-step process. You start by identifying your initial criteria. You generate a trial design. You develop a model representing that design. You analyze it. You get results. And you refine your model, and you keep going until you reach a satisfactory solution. Now, at every step in this process, you have to perform analysis or come up with ground motion records. So there is potential to use technology and use tools to improve this process. And one of the reasons we do response history analysis is, in many cases, we want to reduce some of the uncertainties. We want to reduce some of the conservatism in the code. And so we model the structure to the nonlinear range. Other reasons is we want to better serve our clients, especially on existing buildings. Being able to model the building in detail may help us avoid very costly repairs. We want to offer more information about performance-based design. How does a building perform after an earthquake? How much can you limit the drift? Can you limit the non-structural damage, say for a hospital? And this also falls under reducing life cycle cost. So usually where you start with response history analysis is the ground motion. And so we've been developing a new method of selecting ground motions. And if you're familiar with ground motion selection, people use one of two methods. You either select ground motions and scale them, or you select ground motions and spectrally match them. And the method we've developed actually combines both. So it's been developed again at Degenkolb, and it addresses shortcomings of the two methods. I'm not going to go over it in detail because that's a presentation in itself. But the important thing is this has been reviewed and approved by OSHPD. And if you know anything about OSHPD, if you can get something past OSHPD, that's very important. You can probably get it past any other agency. So the records in this method, the records are scaled and modified such that on average you get a perfect match between your ground motion suite and your spectrum. The spectral matching is not done to get a perfect match between each record in the spectrum. So this has the advantage of reducing the modification you do to one record, so you don't lose the characteristics of the record. If you need more information on this, I'll be happy to provide you with that. Just talk to me after the presentation. Another area that we've been going into in order to improve our understanding of behavior is soil structure interaction. And ideally, you want to model as much as you can. You want to model the soil, you want to model the building, you want to get the inelastic behavior of your building. But unfortunately, this is the current state of the practice. For the most part, it's changing. But typically, people just ignore there's a basement, ignore there's any sort of interaction. You fix the building at the ground, and you apply the ground motions. We know that's not enough for many reasons. So companies who are at the edge right now in the industry, they use what the so-called bathtub model, which is basically you assume the building is sitting in a bathtub that is all moving uniformly. So there's no variation, there's no multiple support excitation. And you have springs that represent the soil properties. And typically, the software that is mostly used to do this kind of analysis is Perform, which, by the way, is not capable of doing multiple support excitation. So it has major limitations in terms of how well it can model this problem. Now, moving to OpenSees, which we're trying to do, allows you to overcome some of these limitations and go much further. So one thing you can do is multiple support excitations. You can get better representation of soil springs. Eventually, we want to get there. While modeling the soil, having actual modeling, explicit modeling of the soil may be feasible now in the research, it's still not practical in practice. Because a model like this could take days, maybe weeks to run, and we simply cannot afford to do that, but we hope to get there eventually. To show you the complexity of the models we deal with, that's one of the models we recently did for a very large hospital in Stanford. And if you're familiar with Perform, that's in Perform. And we went through a process to convert this model to OpenSees in order to do this kind of soil structure interaction. So this shows you the kind of roughly the development of the springs. There are methods in ASCE 41 and other documents that you can follow to come up with the spring properties. But this is still not something we do on every job. This is something we do on some of the projects and not every project. This is another project that we've done where we looked at the difference between including and not including soil structure interaction. And we get also is the question of, is it better? Am I going to reduce my forces? Is my building going to be less expensive or more expensive? So we're starting to look at that and trying to develop some guidelines on when soil structure interaction would help you, when is it conservative, when it's not. That's a comparison of this building model. And on the right, obviously, you have soil structure interaction included. This is a very stiff building. So in a sense, including soil structure interaction for this building is I'm going to play it again, is similar to having base isolation. Your displacements may be a little larger, but it's going to reduce accelerations and reduce demand in general in your building. We also do a lot of finite element analysis, which is mostly component analysis of connections and so on. I'm just going to show you some images. These are some connections from a building we retrofitted in Oakland. This is a pipeline analysis that we're currently working on. We're looking at the performance of the pipeline due to a fault offset caused by fault rupture. And some additional connection analyses. This is a hunched connection with braces and dampers. So back to response history analysis. Some of the challenges of doing response history analysis for an actual project is that you're sometimes looking at many runs. So this last hospital I showed you, we had to do, every time we modified something in the model, we had to do 160 different response history analyses. 160, why? I mean, we only used 10 ground motions, not 7, by the way. But it'll come in a second. There's many combinations that we need to look at. And if you were to run these in series, you'll quickly find out that you need 100 days to run them all. If each of them takes 16 hours, it's going to be 3 months before you're done. Plus, you're going to generate about 30 to 50, actually about 2 terabytes of data. Lots of data to deal with. Not only it's a lot of data to store, but it's a lot of data to go through, analyze, pull out the data you want. You probably want 1% of this information. You don't want the full histories. You want the peaks. So immediately we started to see that we need to develop tools that reduce this complexity. And you can think of these tools as being on 3 different levels. One is the generation of the model itself. We need to be able to generate these nonlinear properties quickly. We need to use parallel processing. And one way or the other, we have to make it work. Whether the software supports it or not, we have to run things in parallel. We also need tools to post-process these results very efficiently. So since we've been using Perform, Perform is not really very friendly in terms of allowing parallel processing. So we have to fake it. We have to basically run individual analyses on multiple machines and create a virtual parallel processing machine. Now, currently with virtual servers, that's a little bit easier because you can just create multiple virtual servers without needing to go between machines and actually run analysis. So these machines allow you to allocate resources in a very flexible way. You can allocate cores and memory to them very efficiently. So for example, if you have 7 ground motions you need to run, you end up running 8 instances, and in this particular case, they're divided between 2 analysis machines with 4 cores each. So each core would run 1 model. And somehow you need to go back and reassemble the results because they're each sitting on 1 different machine. You need to bring back all the results together. So, multiply this by 16 or 20, and you see you have a data management problem. And this is how some of these cases multiply. So we have 10 ground motion pairs, but we need to consider mass eccentricity. So you have 4 cases, 2 in each direction. And Ashpad makes you rotate your ground motions after you run them. So that's another 2 cases. And then you'll need to look at upper and lower bound soil properties. So that's another 2. That gives you 160 runs. And that's not even counting any runs at the MCE level. So if you have to make runs on the MCE level, that's probably another 50 50 runs to add to that. So using these parallel processing methods, you can reduce the total run from 100 days to about 2 to 3 days, which is acceptable, but we still would like to do better than that. So one tool that we've developed is called the Degenkolb Design Database tool, which is basically a very efficient software program that goes through the results and analyzes them in parallel and pulls just the information you need. And while something like this may not be that badly needed with OpenSees, because OpenSees has good reporting capabilities, with Perform, it's a must, because all results are dumped into a big binary file. And to go and process these results through the user interface would probably take you a year to do. So this is the process as we see it. You have the analysis software, and you can plug any analysis software there. It doesn't have to be Perform. You need somehow to run the analyses, do your parallel processing, you get the results, and there's a lot of post-processing on the end. And some of this is similar, regardless of which software you're using. So we see this as developing tools that connect the dots between these software. And so we're developing database tools along with other kind of tools to bridge this gap. We're developing tools to post-process results. So this is a tool that looks at drifts and can give you a summary of your drifts for all your records. So once you've run all of these analyses on multiple machines, you can then go back, bring them together, and look at the drift over these all these models. We're developing specific model management tools. So very often we have the issue of running the same model many times, or variations of the same model many times. But we also have the problem of keeping multiple models in sync. So we usually have a nonlinear model in Perform or OpenSees. We have a linear model in ETABS because we need to design our gravity system somehow. And we may have other models. And you also have your Revit model, which is you use to generate your CAD drawings. So keeping all of this in sync becomes a big problem. Usually this problem appears very clearly when you're close to a deadline, because somebody remembers at the last minute that they didn't update their gravity analysis results or their podium analysis results. And they go back to update their calculations and realize that this model is a year old and was never updated with the OpenSees or Perform model changes. So this is obviously a problem. So we're looking at developing tools again to take care of that. So on the analysis automation side, there's this tool that would basically manage. It's really a parallel processing load manager. It's in charge of scheduling jobs and being aware of all the analysis infrastructure that's available, all the analysis machines. It takes all the jobs that you have and assigns them to the right analysis machines. It's nothing groundbreaking, but the customization of such a tool to various software that unfortunately still do not support parallel processing is the key here. On the model management side, we're developing a model exchange tool, and this is a tool that will be able to exchange model types and convert between different types of models. So you can have ETABS, you can have SAP, Perform, OpenSees, even BIM or Revit. And that's a kind of a schematic of how it would look like. It would be a central tool that you could use to convert between, say, an ETABS model, a Perform model, an OpenSees, or building Tickle. So back to OpenSees. Like I mentioned, we've been trying to slowly move to OpenSees. We've had some issues in the process, but we're still determined to move to OpenSees with Frank's help, who's been a great help. Sylvia, like I said, who's on our team, has a lot of experience. So again, this is a model that we use to convert to from Perform to OpenSees. We had to write some scripts that would take input files from Perform, convert it to OpenSees. Not a trivial problem because the input is very different. But that again goes into our set of, hopefully will go into our set of tools to do that. We've been using some multi-support excitation in OpenSees. So again, back to building Tickle. This is again the tool that Sylvia developed while she was at UC Berkeley. It's a simplified user interface, which is something that's one of the weaknesses or things missing at the moment in OpenSees is the lack of a user interface. So Sylvia developed this user interface which still has a very strong scripting component to it. So you can use a menu-driven interface to do your model definition, and you can also, if you prefer Tickle for some reason, you can still input things in Tickle. And again, one of the advantages of it is it's a slightly higher level of interface. The basic Tickle language in OpenSees deals with material models, deals with sections, with columns. The building Tickle interface deals more with buildings. So you're talking about a frame elevation, about a plan of a building, and it allows you this higher level of looking at a building that you can use to build the model much more quickly. So you can define the typical things you can define using regular Tickle, like sections and so on, but the interface is slightly different, the language is slightly different, define loads. Obviously the main improvement in it is it has a viewer, so you can look at your structure, you can spin it around, look at it from different angles, look at it in 3D and 2D, load a model, save a model, define materials. The things you would expect to be able to do in a user interface for a software. One of the neat things is you can visualize your material response inside of it. How many of you have used Building Tickle? Anyone? Okay, that's interesting. 1, 2. How about OpenSees? Who has used OpenSees before today? Okay. Any other user interfaces that you've used? No? Just plain old Tickle? Okay. Because there are other tools. OpenSees Navigator, is that still around? Yeah? And there are third-party tools, but I'm not talking about those today. You can look at elevations. Certainly, it's a good way to get started if you don't want to learn the Tickle language. Gotta be careful, though. I mean, it's not 100% perfect, so you need to go back into the code and make sure that things look okay, that all the numbers look okay. You can run and control the analysis from inside of it, which is nice. And obviously, the main advantage is you can look at your results visually, graphically, in the interface. And that is very valuable.
Sorry, is it applicable for all of the program, or maybe it has some special template? For example, you can model all of the structures, and you can import all of the programs to this software or not. Because OpenSees Navigator, it has some limitation and some.
So what's the question? I'm sorry, I didn't follow.
I want to know that this software can include and can cover all of the systems. For example, maybe you want to add 2 systems to each other or some other.
You mean multiple material models or multiple elements?
Because as I understand, OpenSees Navigator is only for some templates. For example, you cannot, for example, add 2 systems to each other, and it has some limitations. I bought this software.
Yeah, well, obviously, if there's a new material model or a new element that's added to OpenSees, it's not going to be directly available in it. It has to be updated to include it. In terms of further detail, I'll have to get back to you on that. I'll have to have Sylvia get back to you on that, basically. So if you want to use it, you have questions, I think you can. Is Building supported by? No. To Sylvia, so you didn't have to email Sylvia. And so we actually, one application of Building was in ATC 83, we used it to verify the methodology, and we compared the results to an actual recorded record from a building. So that we actually have practical application of both soil foundation and structure interaction capabilities in OpenSees and of Building using in the ATC project. ATC 83 is a project that was looking at and giving recommendations for doing soil foundation structure interaction. It's going to be out soon. I don't think it's out yet. The report is in draft format, but it should be out very soon. So if you're interested in soil foundation interaction, be on the lookout for that. Okay, so finally, let me start wrapping up. Why do nonlinear response history and analysis? It's a lot of work. It's tedious. In practice, many often you can design a building without having to go through that. So why do we do it? Sometimes it's required. If you have a base isolated building, you have to do it. We don't usually know if it's going to give us a better answer. Sometimes it gives us an answer that we don't like. So we just have to be careful. It's going to be definitely more expensive. And sometimes we can avoid doing it by fixing the problem we're trying to solve to start with. So very often we use response history analysis in practice because we are not meeting one requirement of the code. And doing nonlinear analysis is one way to go around that. Well, sometimes it's easier to fix the problem than to do the analysis. It's not going to make the analyst happy, but that's the reality of things.
Excuse me. How would you know to produce whether or not to produce a better answer without running the analysis?
Well, that's one of the problems. You don't. Sometimes you have a sense. So through experience, through maybe some initial studies, you can predict what the benefit will be. But sometimes you may overestimate the benefit. So there may be still a benefit, but you may have overestimated the benefit because you may discover other things when doing it. It's a much more detailed approach to designing a building. And compared to the way you would typically design a building, there are some systems that would benefit more from doing this kind of analysis from just a strength and ductility perspective. You can argue that. The code at the moment allows you a greater limit on allowable drift if you use nonlinear analysis. So it allows you a 25% increase on drift. So that's great. So you can design your building to be less stiff if you use this advanced analysis. You can use lower omega factors, which are the overstrength factors. That's a factor of safety on the failure of force-controlled elements, brittle elements. If you don't do a detailed analysis, the code forces you to use a safety factor of 2.5 to 3. If you do use an actual analysis, you can reduce that. You can be down to as low as 1.5 or lower. So that can be a lot of saving. You can definitely do a better job in terms of accounting for the actual ground motions, and we've showed some of the methods to do that. Obviously, when you take an exception to the code, you almost always have to do this kind of analysis. So the benefit is you can take exceptions to the code. You don't have to use every single word of the code. This is especially important for existing buildings where you can't just say, I'm going to change things. It's existing. For podium structures, it's still a problem to use because very often it's very difficult to model the full building. This is when say a steel building is sitting on a large, say parking structure or podium structure that's usually made of reinforced concrete walls. To model the full thing inelastically is still very expensive in many cases, but there's no easy way to really do a two-stage analysis. We've tried that, but it's very problematic. This is one example. This is a CPMC Cathedral Hill Hospital. This thing doesn't exist yet, but it's been in design for a long, long time. And if you listen to the news at all, you probably heard about this. It's always in discussions in San Francisco. It's a hotly debated issue. But we've used nonlinear response history analysis to significantly reduce the size of the system on this building. And it included the innovative use of wall dampers, which you see in the picture here. And these wall dampers were the owner liked them because they're less disruptive than typical dampers. And you can see it allowed us to significantly reduce the cost of the system. So 95 million for a conventional system and 67 million for this system. And you see a couple of different systems also that we studied. So this shows you that in many cases you can save a lot of money. You just need to be careful not to overstate it. One of the issues with the nonlinear response history analysis is at the moment the code doesn't tell you how to do it. You basically use your experience and you have to get it approved by a peer review panel. But each peer review panel can do its own thing. There's no set, there's not a set of requirements that is common. There's a chapter in the code, but it's very short. It almost doesn't say anything. So we're currently working on developing, basically expanding that chapter of the code, developing a proposal to do that. There's a BSSC task group that's doing that. Our group, our NTG group, happens to have actually 3 members on that committee. I don't know how that happened, but we all ended up on it. It's in progress. We hope to have it done by the end of summer, at least have a draft of it. We think that's going to be helpful to set some background for how to do that kind of analysis. So in terms of lessons learned throughout our various experiences with different projects, this is very time consuming. It takes time to run, but more importantly, it takes time to learn. If you have new people, new engineers using it, can be very time consuming to do. Steel is easier to do than concrete typically because it's usually possible to use lumped plasticity models with steel without much loss of accuracy. With concrete, that's usually not the case. You have to use fiber models in concrete columns or fiber models with walls, which can be much more expensive to run. Not that you couldn't do it, but it's more expensive. And you have to be careful about your assumptions, viscous damping, mass eccentricity, and so on. And don't overstate savings to your client. So we had a situation recently where the design team kind of was a little aggressive in stating the benefits of doing that kind of analysis. And even though we ended up saving the client a lot of money, if it's less than what you promised initially, you're not going to look as good. So be conservative in how you state the benefits. In terms of software to use, like I said, we use Perform. We are also always monitoring how it's going and whether it's going to be supported in the future or not. So that's an important thing. If you're over-invested in one technology and changes or is not supported in the future, or CSI decides to discontinue it, that's going to be a problem for us, obviously. OpenSees, you know, it has similar concerns. How well supported and how much more development is going to happen in OpenSees in the future is also a question. We're really looking ideally to be able to run our analysis overnight. Ideally, you would set your analysis running at 5 p.m., go home, come back in the morning, and not only find your analysis has run, but you also find a report of all your results. So you would have software running in the background that pulls out the results, analyzes them, presents you with a summary of results that you can then take action on and change your design. And that's the direction we're moving into by developing the tools that we're developing. This will require that we move to the cloud or to virtual machines as an intermediate point to be able to run all this analysis basically overnight, which means each ground motion will have to run on a separate core. We can't run things in series anymore. But this opens up a lot of possibilities for us. We currently do a little bit of sensitivity analysis, some lower bound and upper bound analysis. Once you have the ability to run a lot of models simultaneously, you can start looking at dispersions, at the effect, basically doing sensitivity analysis on a less limited, let me say, number of parameters. Within something that's not parallel, like OpenSea, so for example, Perform, since it's not parallel, you still have as a limiting factor, the time it takes to run a single record. If that takes a week, you can't really run in less than a week, because that cannot be run in parallel. So that's still an issue, which means that you're limited in what nonlinear features you can have in your model. So flexible diaphragms, fiber models and walls and so on, these increase your runtime and you may be limited in their use. So in terms of the needs, what do we need going forward? Time, like I said, we need to be able to optimize the simulation to run it quickly. We need to integrate with BIM, with our whole process of developing buildings and developing documentation for them, basically drawings. And the ability to synchronize between different models is would also be nice. Doing multiple analysis and parallel analysis, model management, being able to look at uncertainties and sensitivities, integrating the analysis into design tools, and so on. Validating and verification of models becomes important as you do things in a more automated way. And we need to keep the engineers educated. They can't just use these as black box software. And data management and visualization, I think that's going to be very important. So with OpenSees specifically, some of the benefits that I see in OpenSees is it's open source, as you know. It has some robust capabilities. It includes the latest research. You can add your user models. I've never done it, but I assume you can do that and it shouldn't be too hard. You can do multiple support excitation, soil foundation, structure interaction, and soil modeling. This is one main reason we're trying to move more into OpenSees. I think there's another presentation on that. And the fact that it's parallel by design is something nice. And it doesn't suffer from other limitations like the recording and output limitations of Perform. And the fiber models are certainly a nice capability. Some of the limitations or challenges, which hopefully will change, is how stable is it? How good are the solvers, or how much tuning do you have to tune the solver so you get a good result? And how the latest research is actually incorporated such that the models are checked, they're stable. You don't just put a model in and it ends up breaking your analysis. Until now, we haven't really had a lot of success with reinforced concrete wall models. We've been able to model columns and beams using fiber elements, but for walls, that has been an issue. But Professor Filippo has a new model that he talked to us about, and we're very optimistic about. So we're looking forward to that. On a basic level, there are some analysis capabilities that are missing that I've been bugging Frank about for a long time. like simply model analysis. I mean, you can do model analysis, but model analysis as used in the code, so using model combinations, would actually be very helpful to, if you're doing verification with another software, that's helpful. And finally, the one big item for me is visualization and user interface. OpenTCL is good, but we need something more robust. Questions? Yes?
Well, you mentioned you were trying to port models from one software into another. If you've done this in the past, have you found the results to agree if you created the same nonlinear model into different software?
No.
How much of a difference do you normally see?
More than I'd like. We've been working on a very simple model recently, and Aaron knows. Aaron has been our intern for this summer, and we've been working on modeling a frame structure for the blind prediction competition for the World Conference. And we modeled something in OpenSees and SAP, and we were having a lot of problems having the two match. Now this has more to do with SAP than it has to do with OpenSees. SAP, we're rediscovering why we started using Perform in the first place and not SAP for nonlinear analysis, because SAP just has a lot of problems. But it's a problem, it's an issue.
But if you do have so much of a difference, how much can you really trust the results of analyses that you produce to design a building to begin with? In any nonlinear time history analysis?
That's a very good question. It's a fundamental question. And it really humbles you and makes you question, at least the number of significant digits you use when you report the results. When you're reporting 1.23% drift, and you go back and compare two different software and you're getting differences of 40%, it puts things in perspective for you. Now, I would assume that if we get beyond the obvious mistakes and obvious shortcomings of the software and bugs and so on, that these results should come much closer together. But that's something that we need to keep in mind about. You can also get the same thing within the same software, just doing some sensitivity analysis. So if I modify my strength by 10% or by 5%, or if I have asymmetric strength or stiffness, how does that affect my results? If that affects my results significantly, that's also telling me that I'm missing something. Other questions?
No questions, well, thank you. Now a country break.